Yeah, it's minus 10 almost. So we should be outside and try to do soap bubbles. You've seen these videos, right? Yeah, how you have a soap bubble, like if you blow a bubble and it freezes instantly, and then it should look really cool. I think it should be the temperature outside. But since we're here, we could as well have a look at the quick summary of last week, where we concluded on the Ginzburg theory, statistical field theory, and we explored the role of fluctuations, as fluctuations tell us where our mean field occur in the framework of statistical field theories, the saddle point approximation, which it brings us back to the mean field theory, where it fails. And so so we looked at fluctuations around the saddle point. And so just for completeness, let me sketch again. So we have the mean field, which is a uniform field, which we seek as a solution for the saddle point, the state that is contributing most to the statistical ensemble, which we say is aligned along the x-axis, and then we look at fluctuations that are longitudinal, which means along the axis of the uniform mean field, or transversal ones in all the other dimensions that are perpendicular to the structure. So these are the longitudinal and transversal. And then we find that the effective Hamiltonian, we recover a Hamiltonian for the mean field, which is this one, and then corrections due to fluctuations, which take the form of Hookean springs, potentials. And we can see that these, what determines the correlations in the system is correlations lengths psi L and psi T, depends on the reduced temperature in a way as the scaling was T, is minus T. And most notably for the transversal modes, we also get a linear scaling with T above the critical point, but no dependence below, which is due to, this is the Goldstone modes. This is the symmetry breaking. This allows us to generate these transversal modes. And so what we now digged in is to say, like, okay, so can we actually measure these fluctuations? And so indeed we can. Namely, we can measure them in scattering experiments, where the scattering amplitude as a function of the wave vector is actually directly proportional to the correlations, autocorrelations of these fluctuations, again in Fourier space, and these then relate to k psi squared plus psi c alpha minus 2. And so if we plot this scattering amplitude as a function of the wave vector, like in V space back in X, sorry. We find that there is indeed for long times an exponential decay with governed by psi. So this is alpha noting that this is indeed, we can interpret this property here as a correlation. And then we looked further into the role of fluctuations to determine both the lower critical dimension and the upper critical dimension. The lower critical dimension we took a different ansatz in the role of fluctuations. Namely, we described the magnetic field as a field that is has a constant amplitude and an angular dependence only that now depends on x. So this we take as a constant. And then we find that the correlations of these angles for large distances has the following behavior. It's either constant, so we found that these angular correlations change their scaling behavior as I transition across d equal 2, the dimension of 2. And so how we can interpret this is that for dimensions of 2 and smaller, we have a continuous symmetry breaking, which is due to these Goldstone modes, these slowly varying angular variations, and they're too costly for larger dimensions. Oh, d equal bigger than 2. Sorry about that. So we find that if we have a continuous symmetry that can be broken, Goldstone modes, the lower critical dimension is 2. And if there's no continuous symmetry, but only discrete symmetry, then the lower critical dimension is 1. And then we went on to look into a new concept, the upper critical dimension. So where here we now return back to the framework of writing down fluctuations around the saddle point, which is why I copied them down here. And we now use this effective Hamiltonian to calculate the free energy. And from the free energy, the response function, to learn how the response function changes as a function of the dimension. So here we return and we looked at the specific heat and found that the specific heat can be written as 0 plus d over 2 for above the critical point and 1 over 8 mu plus 2 . low critical point. And I particularly like the kind of reasoning that we can derive from this simple result. First of all, we can recover the classical mean field results, which are the ones that we have here without fluctuations, which I call, this is C mean field, and these are the corrections due to the fluctuations. And now the real instructional thing, which I hope you really take from this exercise beyond the interest in what's the role of fluctuations in the upper critical dimension, is like, how can we actually learn something about the dynamics by just staring at this integral without actually putting it in a computer and calculating it and taking limiting cases and trying to make sense of this integral, but just looking at it. So by just looking at it, we see where how it can behave. Because what we here actually have is like we're integrating about a d-dimensional space, so we can rearrange this integral in sort of like, you know, polar coordinates to write this as integrating over dq cubed d minus 1. 1 over k q squared plus t squared. And we're integrating over the Brillouin zone, so we're going from 0 to the boundary of the Brillouin zone, which is 1 over the lattice spacing. And so the cool thing is now here that we can really readily read off the limiting results of this integral without actually opening Mathematica or like in a single line. We see that this scales, this is 1 over k squared times for, so we see that we here have a q to the 4 that's contributing, and here we have q d minus 1, so that makes, and then we can see that this only makes, and there's another q here, right? So it's q d to minus 4 is the value of the integral. And if we're at the boundary of the Brillouin zone, then it's really the value of the integral is dominated by this boundary. So we arrive at a4 minus d for d larger than 4, which is where this boundary is dominating, and similarly in the opposite limit we find this integral to be denominated for that. So we see a change in the value of the integral as a function of the dimension, with really strong impacts, because what we see is that, remember, this integral is the correction due to the fluctuations. And so above 4 dimensions, it's just a constant. So there's just a quantitative change to the mean field result, but not a qualitative, which is different for smaller than 4 dimensions, because here we all of a sudden get a divergence at the critical point where t goes to 0. And so we learn that fluctuations change the critical behavior in d smaller than 4 dimensions, while for d bigger than 4, mean field behavior is qualitatively right. And this defines now the upper critical dimension, which tells us above which we expect mean field results to be true. And last, we had the Ginzburg criterion, which told us when actually, at which temperature do we have to be to observe these corrections in the behavior of the specific heat. And so we observe them when the correction due to the fluctuations is bigger than the change in the specific heat, the jump in the specific heat as predicted by mean field. And this we can rearrange to derive temperature below which sorry, that's a C. We expect T smaller, sorry. That's correct. So for temperature smaller than this critical temperature, we expect these fluctuations to show. And what's really governing this when it doesn't show is this variable here, which is the coupling length scale. So here we recover really how intrinsic properties of the system govern their behavior. And here below TG fluctuations shown. So far, I introduced you to various analytical concepts to derive properties at phase transitions, but in reality, you would always complement your endeavors with numerical simulations to check your analytical results and to go beyond the range of parameters that you can explore theoretically. And so that brings us to today's topic of Monte Carlo simulations. Where we're going to talk about importance sampling. And if I manage, I get into going to talk about Markov chains and derive detailed balance. So in a way, this is already a journey into concepts that you would learn in depth in if you're taking the class on stochastic processes, and but they're really ingrained in how we can numerically solve like an Ising model on a computer. So that's why I'll give you this short introduction into Markov chains and detailed balance here. So let's get started. And here we're following Yeomans, chapter 7, Chadori. And also actually, if you want to have hands-on examples, Jim Fessner's book, also it's linked to a website, and you can download some sample codes, some sample Python codes. I think it's Python, where you can just run your own Ising model and just download, and you can change the temperature of the system or the coupling strengths and just play with it. So that's available. If you search, if you look in the book, I think the link's in the book, but also I think it's linked to Jim's website as well. So what is Monte Carlo, right? I mean, what's your first association with Monte Carlo? Maybe you heard it a bit before in the context of physics, but your first association should be Monaco, right? Monte Carlo, like casino, gambling, this, slot machines. This is what should probably pops up in your mind, or at least popped in your mind up in your mind 5 years ago, say. And that's the right intuition. So what you should have in mind when you think about slot machines is that it's a random game, right? And so it's this randomness of playing with slot machines that is captured by the term Monte Carlo simulations. So that's the only link there is. And behind it hides a numerical approach to study equilibrium statistical systems, equilibrium properties of statistical. And it's really widely used by now for continuous spin systems to describe fluids, polymers, disordered materials, lattice gauge theories. I could go on. So really, it's a very fundamental method that I feel you should know about. And I personally, for example, when I did my master thesis, termed diploma thesis at the time, I was interested in the shape of DNA, which is a semi-flexible polymer, which means it's a chain that has some bending stiffness. And if you think about DNA, it's in a cell, so it's subject to a lot of thermal fluctuations by the heat provided. And I want to know what's its shape. How does it curl up or not curl up? And so to study that, I'm interested in the equilibrium properties of this chain of like this elastic polymer subject to thermal heating. And so I'm interested in the equilibrium properties of a statistical system. And so to learn about these systems, I did sit down and write a Monte Carlo simulation. So it's really a very standard tool that you use way beyond like Ising models, where you can just download the code. But it's really a very, very versatile approach that I guess you will always come about when you want to, when you're interested in some equilibrium properties of a system. That said, so for today, I will introduce like the sort of theoretical background. And on Friday, I will try to teach you really the when you implement it. Like I won't go into an implementation, but I will teach you the concepts of what you should be aware of when you're implementing a Monte Carlo, because it's a little bit like there's a lot of cooking involved, right? In a sense, and like, what is the challenge about cooking? I think the challenge about cooking is the vocabulary that you need to learn, right? Because people tell you like you have to poach an egg, and then you know what an egg is, but what the hell, right? You know, it's the vocabulary. And so that's what I'm trying to do. On Friday, I'm trying to teach you the vocabulary so that if you sit down and want to write a Monte Carlo conversation for whatever, you at least know, like, this is the vocabulary that I should look up and pay attention to. That's the idea. Okay. And the goal that we have here is to find the average value of a thermodynamic variable. And just to stay in the context of this class, let's think about magnetization. And so, okay, so what would we be interested? So how do we write down the average value of this thermodynamic property? Well, you know, the average would be summing over all states of a system of this property divided by the partition function. Okay, so I want to know, like, say A, which could be the magnetization, but could also be like the average size of my polymer. So how can I calculate that? Well, you know, I can write a simulation. I think of a spin lattice, and you know, I take a spin lattice and I just enumerate all states, right? I can just go through like and you know put down all variables. That would be the naive approach, and is doomed to fail, because just the mere enumeration and calculating this property on a lattice is something that even our computers will run out of capacity very, very quickly. Okay, so we enumerate all states and calculate A. And for an Isaac model, on lattices with n sites, this would mean for the Isaac model we have 2 to n states. And direct evaluation is only possible here then for n roughly the size of 40. Okay, this is a disclaimer. This number I took from Yeoman's book, which is a tad older. But you know, okay, so maybe it's 80 now, right? But still, I mean, the gist that you take from it is limited, right? I can only explore systems of a specific size, so that's very sad. And so the idea of Monte Carlo now is to exploit the sequence of random numbers to randomly sample the system and thereby do a better and more efficient way of attaining the averaged, you know, the statistical ensemble of the system. So the sequence random variables, random numbers, sorry. Just as and just as a side note, I think it doesn't come up anymore nowadays, but like in the 20 years, 15 years ago, just and much more earlier, just the idea of really do I have random numbers was a challenge. The idea that, you know, I'm going to explore random numbers to generate states in the system. And to really have no bias, I really have to make sure that these numbers are really random. And this is like, you know, along the lines of cooking recipes, but I think it's hopefully outdated nowadays. But really, like, I still used to check that my random number generator is really giving rise to random numbers, and there's no biases, because you know, if you only have a certain storage capacity of random numbers, then you are bound to sort of run in circles, and you may introduce biases in your simulation. So, like, just as an idea that there's really a lot of cooking that we sort of formally take for granted, right? I mean, we just I don't know, and see it's rand, or like we just draw this random number, but it's actually something that have to think about, is this, where does it come from? How is it generated? Is this really random to the accuracy I need? All right. Okay, so we want to use the random numbers, and the easiest approach is a so-called heat bath Monte Carlo. And the idea is that we want to find a thermalized state, and we would do it in the following way. Just write it down. It's exemplary for the Ising model. What we would do as a first step is initialize a random spin state on a lattice, right? We assign just a random spin up and spin down on all sides on the lattice. And then we run the heat bath by first picking a side I at random. And then we check how many neighbors are pointing up. So that would be calculating the local magnetization by summing over all neighbors of I, and that can be either 4, 3, sorry, not 3, sorry. We're thinking about square lattice 0, -2, -4. So that would be 4 neighbors pointing up. Three pointing up, 2 pointing up, the rest pointing down, obviously, 1 pointing up, 0 pointing up. So this is just enumerating the spin, the magnetization, and then we can use the magnetization to calculate the energies. So we then calculate E plus as -J mi minus H. This would be the energy for our spin I being +1, or E minus as J mi minus H, plus H for spin I -1. Okay. And so we're doing these calculations because we want to thermalize the system, and so we want to see if for which energy of my spin I should it have in its current environment. And so that would be the 2 different versions of the energy of spin I state in its current environment. And then the update is to decide, okay, which state should it be in to be in a thermalized state. And that would be to set the spin I to +1 with probability of e to the minus beta e plus over the 2 potential states probabilities, so e to minus beta e plus e to the minus beta e minus, which gives me the probability to have the spin I in plus state, or vice versa in minus with the probability e to the minus beta e minus. Again, same normalization. And so this is now the calculating the probabilities from the energies and the Boltzmann weights, where our chosen picked spin should be. And then here the Monte Carlo step comes in to now draw a random number. Between 0 and 1. And now if R happens to be smaller than P plus, we send the spin I to the plus state, and else we send it to minus. Note that P plus P minus is 1. And then we thermalize this one spin, and then we keep picking other spins and repeat this thermalization. And so I chose this example of the heat bath because it already introduces nicely the concept of how I thermalize the system by calculating the probabilities of individual states with the Boltzmann weights, and then drawing a random number to put the system in the preferred state, or accidentally also not. Yes.
What's how we do? So we pick a random number between 0 and 1.
Yeah.
And then now it's either if it's smaller than, if this random number is smaller than P plus, then
yeah. So P plus. So for example, if P plus is 0.1, then you're most likely to end up in the minus 1 state, because in 90% of the cases of picking a random number, it will be bigger than P. But there's a 10% chance that you will still pick the lower one. And so the idea is that by choosing this random number, you put in the fluctuations that you're not calculating, an equilibrium state, but you have some fluctuations in the systems that can also drive a spin to be, fluctuating up despite but with a very low probability. And we know the probability because it's given by this Boltzmann weight, right?
Yes. Yeah.
Exactly. And that's the idea to take from this, from the heat bath, because when we look at it, it's a bad scheme all over again, right? I mean, it's not as bad as enumerating all states, but it's still pretty bad, because what we need to do is actually we're only picking one spin at a time, and we're only thermalizing it with respect to its neighbors, and so we need to really pick a lot of spins to actually in the event will have it thermalized, right? And we most likely have to pick spins repeatedly, because the neighborhood of a spin will also change, right? So say you start with a 50% chance of putting a spin up and down, but you're at a low temperature, right? So at a low temperature, you would expect your thermalized state to be mainly aligned in either direction, and just a few fluctuations in the opposite direction, right? This is what you would expect. But to reach the state, if you start with a 50% spin up and spin down, you have to pick a lot of spins to flip them and align them with this protocol. So it's not a good algorithm. We have to do better at getting the statistics nicely sampled, right? So here we thermalize one spin at a time. It's very slow. It has a bad scaling. Put the number. Besides n, and therefore we need better And so what I'm heading here for now is, okay, so we have to be better in sampling the important states or the mostly contributing states of our statistical system. And so we're heading for importance sampling. But just as a comparison, the idea that we had here was what we explored with the heat bath example was to have random sampling, where the idea is to randomly. Okay, so no, okay, so a heat bath is really like the idea of thermalizing one state at that time. But what I can do is now, you know, I really want to get the statistics for the system. I don't want to have them enumerate them all, but what I could do is I could just like, you know, randomly draw states. Like I could just say, you know, I draw my spins from a 50-50, a 51-49 distribution, and I just calculate the magnetizations by evaluating the Bordstein, the partition function, right? So I could just do this. I could just randomly generate systems. And then, you know, just take the average over those systems that I generated. That's a bad idea. But just maybe to show the bad example so that you can appreciate the good example. So why is this a bad idea? Well, we actually know from an everyday example, because this is how it feels like how people take polls before elections, right? So there's a whole gamble of like, you know, can we predict the outcome of an election? And what you do is like, you have a random number generating of phone numbers and you call people, and you hope that by this method, you're evenly sampling the population by just calling, I don't know, what about 3,000 people, and that's representative of a population of, I don't know, 40 million voters, is very likely to not work out. But that's the idea of random sampling. And so, yeah, it's not good. So it's a randomly generate state. And the background is it's only good with large statistics. Okay, so but if you take this example of the, you know, trying to predict elections, what you could do is sort of to say like, you know something about the probability of people from this neighborhood having, I don't know, an 80% going to the polls, whereas this neighborhood only like 30% of the population will go to polls. So I can actually include in like the phone numbers that I'm generating, I can include extra information I have, and thereby adjust my sampling to not be purely random, but according to the importance of how a population actually has impact on the poll outcome. Those that, you know, where people go vote to 80% will have a larger impact than those areas where people go vote for 30%. And that's really the idea of importance sampling. And that's now really importance sampling. This is the method that you will use if you use Monte Carlo simulations. Let me introduce the theoretical idea behind that. And we're going to illustrate it by looking at a simple problem, which is calculating an average. Okay, so I have a function f of x, and I want to calculate its average over an interval from a to b. So average means that I normalize by the size of the interval, and now I'm integrating from a to b over f of x dx. Okay, so I don't know this function. I have to numerically do this. So what I can do by simple sampling, I can pick n points, xi, with I between 1 and n, that are uniformly distributed in this interval AB. And then I can calculate my average of f of x to be proportional to the number of points that I'm sampling this interval with, and the sum of evaluating this function at all these individual points. But now say f is a function that is peaked around its mean value. Say it's a Gaussian function, or it's like, I don't know, any other function. That Gaussian we can actually integrate, but any other function, and I know it's peaked. So I know if it's peaked, and actually in calculating the average, those values that are close to the peak will contribute most. Whereas if I have these long tails where the value of the integral is almost to 0, they don't contribute significantly. Dominant. Is close to the peak, and tails significantly. And why is this a problem? Well, the problem is how much computational resources do you have, and how many points can you draw, right? So if you draw too few points, like say 5, and you happen to miss the mean value where it's contributing most just by the interval you chose, you're doing a bad estimate of the average, right? And so typically what you would do is you just having lots of computational resources available, you would change n, make it bigger and bigger until you see that your average doesn't change as a function of n anymore. And then you're like, okay, I'd chosen enough sampling points. I did well. But again, this is assuming that you have the computational resources to just do it, go to a very large n, which is the same idea of, if I could create my system with random sampling, thousands of times to really efficiently sample the state, I would be in game, but this is typically not the case. So we're limited in the number of n, and so this is a problem that we might just happen to miss by the choice we are the important contributions to our average. And so a more efficient strategy would be to sample the function with a certain probability x, which is taking in prior knowledge that we might have about the function. So sample with a certain probability p of x. So p of x would be a positive function that's positive, a function that's positive across the entire range between a and b, and it would be normalized over the interval, so that it's contributing to 1. So just putting in weights. And then I can write my average as 1 over b minus a as before, integrating over a over b. And now I would calculate this integral, integrating the states with this probability p of x. So what we can here, so what we do is, well, we now choose, oh God, our xi, so our n points, according to the probability p of x. So say I know my function is peaked around 5, then I want to create a function p that has a lot of points around 5. And so I'm drawing a lot of x that are close to 5 according to this probability. And then the only thing that I have to pay attention for the normalization to work out that when I'm taking the average, now having these points not uniformly distributed anymore, but according to my p of x, that I have to normalize the function that I'm evaluating with this p of x. So what I do is now I can approximate my average value by again summing over n points, but these are now not evenly distributed anymore, but according to p of x and evaluating f of x divided by p of xi. And so by that mean, I can make sure that I sample a lot of points along, where my function is peaked. And so, okay, but now my trouble is, what is a good choice for p of x? Well, the ideal choice would be to just sample really along the lines of my f of x, right? Because then I would make sure that I really sample those points a lot that are contributing a lot because they are big. And that's the idea of importance sampling. Okay, but obviously here the disclaimer is what I'm assuming is that I could choose this probability such, but what I'm doing here is I need to normalize it to have a probability. And here I'm putting in already that I would know the integral that I'm actually wanting, that I need to calculate, right, to find the average. And so obviously I have to make another choice for the p of x. But that's the idea. And so but I hope I installed with you the idea of why I would like to do importance sampling as the simple example of just calculating the average of a function. Let's now turn to a statistical physics example. So why is it easy in statistical physics? Well, because we actually already know, as it will turn out, right? We already know which states are important. Because this is what our Boltzmann factor is telling us, right? That we know that with the Boltzmann factor, we're weighing those states most that are contributing, having the largest Boltzmann factor. And this is going to turn out to be our probability function for the importance sampling. But let's start beginning. So the idea is now to look at the example of, say, the magnetization in the Eisenmenger. So that's then summing over all states, when the states have a probability PR and a magnetization. And then the P of R is given by minus beta, calculating the Hamiltonian for state R normalized by the partition function. In this context, simple sampling i.e. picking n configuration states would then we go back to the notation as before, right? Where we had where is it? Or didn't have it yet? Oh, okay, so we just go for like now we calculate the average of a function A, right? We would just uniformly sample over all states and just sum over the values of these states. So this would then be given by summing over all the states of a configuration, calculating the property AR at the state. And here we have then summing over minus beta HR, the normalization. And again, we have the same problem that many configurations do not contribute significantly as its PRs are small, right? PR now being sampled with the Boltzmann factor. The probability of the contribution, the weights of a state, giving now by the Boltzmann factor, we know that, for example, if you have states with a very large energy, they won't contribute, right? But if I just randomly draw sample configurations, then I will hit those with a low PR, as likely, much more likely actually, than the ones that are having a low energy and are contributing a lot. And so now the idea of impartance sampling for this function now would be to sample the states A of R, again with a probability that is different P of R, and I'm copying down the rest of it. Oh, it's an R. So now I sample my states N, not uniformly, but I draw my states from a probability distribution that I here call P of R. And while doing so, I have to normalize my the value that I'm, the property that I'm evaluating, A of R over P of R, and same down here. So that's the same idea as doing exactly what we did here, right? Uniform sampling and uniformly distributed points. I would just sum over them, except that for evaluating our expectation value, we have this Boltzmann factor and the value of our magnetization, making our function. And now I switch and say, okay, what I should do is I should draw my states according to a probability function that's better sampling the important states. And so I'm drawing them from this distribution P, and at the expense I have to normalize with this function. And now the natural choice of how to choose this P of R for the statistical system is to have P of R proportional to the Boltzmann factor, right? So if I just take that, I know that the those terms are contributing most that have a large Boltzmann weight, then I can just sample them accordingly, right? So I can just draw my states from this distribution. And so with states Ni now sampled, ability PR, we get that A becomes the sum over the number of configurations because obviously the Boltzmann factors just happily cancel out. And thus, if we switch to the magnetization, it would just be summing over all configurations drawn from the Boltzmann distribution. Okay, so now we know what we want to do. We want to draw states according to the Boltzmann distribution, and then just calculate the magnetization or whatever other property would have according to this. Now the question is, how do I do that, right? How do I actually efficiently draw states from this distribution? We need an algorithm to sample okay. And that brings us to the concept of Markov chains.
Just a question.
Sure.
So is it like, okay, this equation where the A is about 1 over n con, like the config, yeah, right, this. So do I then pick which R I am choosing, or what am I still free to pick in this equation? Like what, when I sample, okay, in the previous example, I sampled in this, like I sampled in the sense that I picked the n points, which is in the sum randomly. But what do I pick here still? Like what's still
no, you do okay. So like yeah. So wait. So here you pick random states. You just like you just let your random number generator run, and you calculate the states, and then from the states you calculate this average probability. But when you do that, you will generate a lot of states that have a low Boltzmann rate and actually don't contribute to the sum at all. And you need to draw a lot of states so that you've sampled enough points where the contribution is large, namely at high Boltzmann weights, to actually have a good estimate of your average. That's the same thing as really think about this. You have a function and it's peaked, and I want to make sure that I really sample these points here in the middle, right? And I actually don't need to sample these a lot because they won't contribute anyway. So if I have a limited in the number of points that I want to draw, then it's actually good to focus on these. And now what we want to do is to sample a statistical ensemble of a system nicely, is to draw our states with a probability given by the Boltzmann weight. So such that we draw more states that are having a large Boltzmann weight and only a few states that have a low Boltzmann weight, because they don't contribute. And say my computation resources only allow me to draw, I don't know, 500 configurations, 1,000 configurations. That's a lot of configurations already, right? Depending on like how much it takes for your system and how many parameters you want to vary and so on. Like this would be a lot, right? I only have 500, say, states I want to draw, and now I want to draw those primarily that have a large Boltzmann weight.
Yeah, but okay, no, the question is, if I now, for example, if I pick a random state like of my system,
you don't pick randomly.
Yeah, but
that's the point.
Yeah, but like in the first one where I haven't done the important sampling
yes.
yet, I just want to understand when I've picked it, then what do I evaluate here? Because I don't sum over all configurations, right? Because I only pick one configuration.
Oh, yeah, but you are, yeah, okay, but I mean,
so
you have to you know, you obviously have to sum over a few states to have an average. Like one draw doesn't tell you anything, right? Because then you didn't average.
Okay, so when I have picked, for example, 10 and just insert in this formula.
Exactly.
Then, okay, now I understand. Okay.
Yeah. So it's like, you know, it's really like if I draw just 10 points that are and I would just take the average. And the problem with these 10 points is that these can be like, I could, if I evenly distribute them, you know, I manage, I might even miss the peak, right? Yeah, and then I have a problem. Okay, but really the challenge is like, how do I now sample these states? And that's brings us to the concept of Markov chains. And the idea of Markov chain is that they provide a biased random walk through the state space, such that we know we reach thermal equilibrium at long times. So if we keep wandering according to these Markov chains in our state space, we'll reach the thermalized state. So it's a biased in a sense, it's a little like the idea of the heat bath Monte Carlo, right? So if I just keep thermalizing individual spins after one after the other, eventually I will reach the thermalized states at long times. I know that I will, right? I mean, the heat bath Monte Carlo, in a sense, it's not efficient, but it will, you know, give me results eventually. And that's the idea behind the Markov chains as well. And so what are the equations that are governing now this random walk, this biased random walk? So say we start, say the system is in a state as which is given by the spin configurations at a time t, and which we describe by a probability. P. So there's a certain probability to be in this state at a given time t. And I'm now looking for a transition rule to go from my state S to a new state. So, you know, I'm in my state space, there are lots of states, and I want to define rules for how I can randomly walk within my state space such that I'm really sampling this state space in a fashion then I achieve thermal equilibrium. So to this end, I define the transition rule that defines the rate to go to a new state as I tilde by the probability to arrive in this new state tilde is given by the probability to, first of all, have been in my state S, and the transition rate between going from my old state to my new state. This is just nomenclature. So here this W is now the probability to transition between states. And now the key is that the dynamics of my random walk are really governed by these probabilities to hop between states. And there's certain constraints that I need to have on this probability to reach thermal equilibrium. My hands are getting cold. It's interesting. Like it's really harder to write smoothly. It's not that cold here, but I'm sorry. Yes. So okay. Okay. So first of all, they need to be Markovian. So far on vocabulary. So that makes up Markov chains. Very important term. So Markovian means that the probability to move to a new state only depends on, it doesn't depend on the past. So like it's really just a transition probability between my last past state and the next state, and not my last. So that history doesn't matter. Probability. There's no memory. So you only know about your current state, and this defines probability to go to the next state. Okay. Second of all, the probabilities have to be ergodic, which means that they allow me to really sample the entire state space. Counterexample would be my probability is defined such that I go in cycles. So my state space is, I don't know, 100 different states. But my probability is set up such that I go from 1 to 2, from 2 to 3, from 3 to 4, and from 4 back to 1. If I have the probability set up as such, I can't sample all the other 96 states and have a problem. So that's the idea of ergodicity, that the system has the probability has to be spanned up such that you can't circle and you can reach all the points. So there has to be no transient states, for example, i.e. that would be states the system spends a lot of time, but then leaves to never return. So that's different than having these cycles. So that would be so this I think it's hard to describe it in for Ising models because they're too simple in this context. But say I'm going back to my DNA circle. There was actually a case. So I want to move my DNA it was actually circular DNA. So I have a set of dots that are connected in a circle, and now I want to have them thermally thermally fluctuate by moving in space according to my Hamiltonian that's defining the equilibrium states. And so I have to set up a way of how I move these points. And I could set them up that, for example, say the motion is confined to a single plane, right? I mean, I could be so stupid to do that while I'm actually trying to sample, the statistics in 3D space. I could set up the movement such that I only sample in the 2D plane, and I sample all these states, but I never allow the system to actually go beyond and rotate to get into the 3D space. So this would be sampling a transient state that, in principle, the system could leave to other states, which are actually really sampling much better the equilibrium state. So I feel like ergodicity it's easy to state, like you have to sample all states of the system, but it's very hard to assess in like when you're in the unknown, right? When you say like, okay, so how can I actually attain new states in the system such that I actually reach all points in the system. But that's why you really have to have this in mind all the time and trying to see if there's a way that you may get stuck in transient states. It's much easier to see that we shouldn't go in cycles. So really the idea would be to one can get from a pre-state Si to every other state Si tilde in a finite sequence of moves, of steps in transition states. Okay. More important point, detailed balance. Detailed balance is described as the transition probability to go from state S to S tilde, given that I was in state S, is equal to the opposite direction, namely to go from state S tilde to state S, given that I was in state tilde. So the probability flux from S to S tilde is equal to the probability from S tilde to S. So what's the gist behind that? So just as a rule of thumb, what this tells me is I want to go from every state to every state along the system. And so if I start in a state S and I go to S tilde, my statistic have to be set up that I'm equally likely to also go back. Given that I arrived in this in the state S tilde. So it could be that S tilde is much more likely to be in than S, but that means that even if there's a smaller probability, like smaller transition rate to go from tilde to S, because I'm in S tilde, much more likely the overall probability flux to go back is the same. And by ensuring this flux is to be the same, we ensure that we sample all states in the system. And that's, in a sense, a much easier condition to check than ergodicity, because there's an equation, right? So there's an equation, and I can just put in and sample. This is how I set up my code. Is detailed balance fulfilled? I can check on that because there's a definition that goes with it, which is much harder for like ergodicity, at least in my opinion. I will just throw this out now, and I will derive your detailed balance on Friday, going through Statistical question.
Is it intuitive that the flux should be the same even if the state S I tilde is much more likely?
So if so the probability flux has to be the same. So the probabilities of different states in the system can be highly different. I mean, that's the whole idea why we do the importance sampling. But I have to still be able to reach all these states. And so to make sure that I reach all these states, I also need to be able to reach these lower probability states because they, with the same overall flux, to make sure that I in principle can sample them as well. And so the idea being that also your probability landscape of your system might not have a single peak, right? So it could be that there are multiple peaks. Say my semi-flexible polymer is equally likely to be in a circular state, but also in a curled up 8 state, right? And in between are states that it's very less not likely at all to be in. I'm making this up. This is anyway. And so I will have 2 different peaks in my probability space where once reached, I will sample a lot. I will sample a lot. But to reach them, I have to go through this valley. And I'm only able to go through this valley if this detailed balance is fulfilled. And then, as I said, formal proof next Friday. Yeah.
But detailed balance and ergodicity are 2 independent
Yes.
conditions, right?
Yeah.
Okay.
Yeah. So detailed balance is a local property in transitioning. Like, it's just telling something about how I transition from one state to the other. Where ergodicity is a global statement of I should reach everything, which I can't necessarily infer from detailed balance. So they're 2 different, like, as I said, detailed balance is local in, like, how do I get from one state to the other? And that's why ergodicity, to me, always felt much harder to check that this is indeed fulfilled when I come up with a system to move about. And just as a rule of thumb, if an isolated physical system is time reversal invariant, so say there's no dissipation, no magnetic field, and the states are also invariant under time reversal, then detailed balance is automatically satisfied. That derivation of detailed balance I'll do on Friday. For now, I will just quickly show you how some different choices for this transition probability S tilde that are possible. Okay, and this is what I said all the time in designing Markovian and detailed balance. Easy to check. Ergodicity. Tricky if you don't know the state space a priori. That's the direction of the jump over for now. So the two standards mostly used algorithms for designing these probabilities are the metropolis importance sampling, where the probability is defined such that I calculate the state of the tilde system, the energy of the tilde system, whether it's the non-tilde spin system, and I take them to the Boltzmann factor, and that's my transition probability to go from S to tilde. If the energy of tilde is bigger than 1, so I'm less likely to go to a higher energetic state, and if the energy of the tilde state is lower, then I totally go there with probability 1. And an alternative would be Glauber dynamics, where I have this being put in one formula minus beta E tilde minus E. And so the standard one, at least for me, it would be the metropolis importance sampling. And this can be generalized in terms of the probability to accept transition. So the idea is I have a state, I do something to my polymer and wiggling them around, and I have a new state that I can generate, and I accept this new state and move my system into this new state according to the metropolis importance sampling. So if it's lower energy, I move. If it's higher energy, I only move with this low probability. And so it can be written in an acceptance probability of a state, which is given by the minimum of 1 versus e to the minus beta E tilde minus E. And if I have a state where the probability to there's different attempt probabilities and like trying to reach a certain state compared to other states, like the what I do to the system to move into a certain direction might be biased, right? That I'm likely to twist my polymer this way, but less likely to twist it the other way, right? So there's a different attempt probability that I will have a bias in the way I can sample the state space because I have to obey certain constraints that are given by the physical system. Then I can change this and have an asymmetric can take account for this asymmetric attempt probability. Say, which I determine here alpha, if this probability to go, attempt probability to go from S to tilde is different to go from tilde to S, then I could also modify this to be 1 if it's lower energy, but here I would have these attempt probabilities taken into account. Tilde state. Sorry, no tilde. And this we'll see comes out of the request to satisfy detailed balance. Okay, so this is where I stop today. Next week, I will give you the derivation of detailed balance, and then we'll do hands-on, like what do I have to pay attention to when implementing Monte Carlo for a system of choice. Yeah, question.
The generalization of metropolis.
Yeah.
Is the factor of 1/2 importance?
No.
There's...
No.
Okay.
No, this is just so that you don't get confused when you compare it to Glauber dynamics. That's why I put it in.
Okay.
Yeah. Because then it makes more sense if you see them next to each other. Yeah. Thank you. Good question. Okay, thanks so much.